In today's tech landscape, Docker has become the backbone of modern development, and it's important to stay ahead. Networking is a core part of Docker's functionality, allowing containers to interact with each other and the outside world. In this course, you will learn why networking is fundamental to containerized applications and how it supports seamless inter-container communication. Whether you're connecting microservices, managing multi-container setups, or troubleshooting networking challenges, this course equips you with the knowledge to create robust, well-networked applications. Please join us in this course on Docker networking, creating, managing, and troubleshooting container networks. Before diving into the exciting world of containers and networks, let's talk about what you need to know to make the most of this learning experience. You should already have a good understanding of containerism. This course will deepen those skills and provide you with a practical application so you can learn more about how Docker networks facilitate communication between containerized services. You should have basic knowledge of Docker, including how to pull images, run containers, and manage them with common commands. If you're new to Docker, I recommend starting with the Docker foundations before jumping into networking. This learning path will guide you through the basics of containerism, building your first Docker project from scratch, and everything you need to know about Docker Compose. You should also be comfortable with moving around in a terminal. We'll be using the shell for a large part of this journey, so being familiar with how it works and what to expect will be useful. If you need to brush up on terminal skills, check out the official Bash Academy guide at Guide Bash Academy to hone your skills in writing Bash scripts. Understanding basic networking concepts is also essential. Things like IP addresses, DNC, subnets, and ports will come up frequently. If you've ever set up a home network or worked with servers, you probably have the knowledge that you need. And finally, you should be comfortable using GitHub. There's a repository for this course, and it includes a cheat sheet with every command used throughout this course. There are further instructions on using this repository in the README. With these prerequisites covered, you're all set to dive into Docker networking, and remember, even if you're a little rusty on some topics, don't worry. I'll guide you through step by step. Now, let's get started and explore Docker networking. What is Docker networking? If you've been working with Docker, you know containers are lightweight, efficient, and powerful. But how do they communicate with each other or with the outside world? That's where Docker networking comes in. Docker networking refers to the system that allows containers to communicate with each other and external resources. It's a critical part of orchestrating and scaling containerized applications. A network in Docker is a virtual layer that connects containers. Docker provides different types of networks depending on how you want your containers to communicate. The most common types are bridge, host, and overlay networks. We'll dive deeper into these types throughout this course. Docker automatically assigns DNC names to your containers. This allows containers to communicate with names like web or database instead of hard-coding IP addresses. This feature is a game changer for dynamic environments. We'll discuss this topic in depth later in this course. When a container needs to communicate with the outside world, it's accomplished by exposing ports. For instance, a web application container might expose port 8080, making it accessible to users and other services. These terms networks, bridge, host, overlay, DNC, and ports form the foundation of Docker networking. Don't worry if they sound complex right now. As we progress through this course, we'll explore each concept with practical examples to solidify your understanding. Next, We'll discuss why all of this matters and how Docker networking is used in the real world. Why Docker networking matters? When you're working on a project with multiple parts, a database, a web server, maybe an API, how does everything communicate smoothly? If you're using Docker, the answer lies in Docker networking. There are 3 key reasons Docker networking is so important. First, modern applications are often made up of microservices. Each service runs in its own container and needs to talk to others. For example, your web frontend needs data from a backend API, which might pull from a database. Docker networking makes it seamless for these services to communicate whether they're on the same machine or across a cluster. Next, scaling. When traffic to your application grows, you might spin up additional containers to handle the load. With Docker networking, you can add or remove containers without manually reconfiguring how they communicate. Networks like overlay networks are perfect for this dynamic scaling. Security is another major reason Docker networking matters. By default, Docker isolates containers from the outside world, which is great for security, but you can fine-tune your networks to allow only the traffic that you need, like exposing a web service on port 80 while keeping the database private. Docker networking is more than just a tool set, it's a critical piece of containerized application design. When you master it, you'll gain the confidence to build scalable, secure, and efficient systems. In the next section, we'll dive into some basic Docker networking commands. Basic Docker networking commands. Now let's talk about some basic Docker networking commands, how to use them, and where they fit in real-world scenarios. I'm in the terminal that's available in Docker Desktop by clicking the terminal option at the bottom right of the screen. To create a network, use the docker network create command, followed by the name of your network. In this case, I'm naming it my network. To list all networks on your system, use the docker network ls command. This will show your network's name, driver, and scope. Notice how the type for this network we just created is set to bridge. This is the default network type used if the type is not specified. We'll talk about the different network types later in this course. Now, let's run a container that's attached to our newly created network. To do this, we'll use the docker run command and name the container myinc. We use the network flag to assign my network. The D flag will run the container in detached mode, and we'll use the P flag to map port 8080 on the host to port 80 in the container, and we'll use the inc image. You can verify that the container is running in Docker Desktop. Click on the link for the port mapping next to the running container in Docker Desktop, and the inc welcome page should show up. Alternatively, we could have used the docker network connect command, passing in the network and container names. The error message here means that the myinc container already uses the network we created. This only works on existing containers. If you want to remove the container from the network, you would use the docker network disconnect command with the name of the network and container. You can get more information about the network we created using the Docker network inspect command and the network's name. This provides invaluable information, including the name of the Docker network is my network, when the network was created, the scope of the network, in our case, it's local, the network driver used for this network, which in our case is Bridge. The Docker Network Inspect tool is something we'll review in detail later in this course. Now let's stop and remove our running container. You can do this in Docker Desktop by clicking on the delete icon to the right of the running container. This will completely remove this container so that we can move on to the next step, which is removing the network. Finally, to clean up unused networks, you can remove them using the docker network rem command with the name of the network you want to remove. Just make sure that no containers are connected, as this command will remove the network, regardless of whether it's being used or not. To verify the network has been removed, run the docker network ls command again. Now that we've covered the basic Docker networking commands to create, list, inspect, and remove networks, you will have a challenge to put these skills to use in the next section. It's time to test your knowledge with a challenge exercise. For this challenge, you'll create a bridge network, verify that the bridge network was created, and run a container and connect it to the bridge network. First, create a new bridge network named MyBridgeNetwork. We'll use this network to run a front-end container in a minute. Verify that the bridge network was created by listing all networks created on your system. Note the network ID and verify that the driver is bridge. Next, run a container and name it frontend. Connect it to the MyBridgeNetwork we just created. Run the container in detached mode. Map port 8080 on the Docker host to TS port 80 in the container. And use the inc image. That's it. Now let's review the solution for this challenge. First, I asked you to create a new bridge network named MyBridgeNetwork. The answer is to use the docker network create command and pass in the name MyBridgeNetwork. Since Bridge is the default driver for Docker networks, you do not need to specify that network type. The next exercise was to verify that the bridge network was created by listing all networks created on your system. You do this using the docker network ls command. This will list all networks that have been created on your system. You can also verify that the driver is bridge. Next, I asked you to run a container and name it frontend. This is done using the docker run command. Connect the container to the MyBridgeNetwork using the network flag and the name of the network, which is MyBridgeNetwork. You also needed to run the container in detached mode, which is done using the D flag. Mapping port 8080 on the Docker host to TS port 80 in the container can be accomplished using the P flag. And finally, use the inc image. That's it. In the next section, we'll look at the different types of networks. Overview of common Docker network types. Docker containers communicate with each other across servers and even with the outside world. But how is that done? In this section, we'll review the 3 Docker network types in detail and learn how each one plays a unique role. First is the bridge network. For example, MyBridge. This is Docker's default network type. When you create a container without specifying a network, it's automatically placed here. Containers on the same bridge network can communicate with each other, in this example, DB and web, but they're isolated from the outside world unless explicitly configured. Containers are sandbox, meaning external systems can't directly access them without routing. The bridge network sets up a private network on the host, allowing containers to communicate while blocking access from other Docker networks. In this diagram, our application is now live on port 80 of the host. Thanks to the Docker bridge, the web container seamlessly communicates with the DB container by name. Docker creates an isolated network for containers with their own private IP addresses. Behind the scenes, Docker handles everything, creating Linux bridges, managing IP tables rules, setting host routes, and assigning private IPs through a built-in EPAM or IP address management driver. The next type of Docker network is the overlay network. These are useful when you're working with multi-host networks. They allow containers running on different Docker hosts to communicate securely as if they're on the same network. In this example, we have two containers, named DB and web, deployed on two separate Docker hosts. Our web app is still running on port 80, but now it's deployed across multiple hosts. The Docker Overlay Network driver makes multi-host networking simple and seamless. As a swarm scope driver, it operates across an entire swarm or OX cluster, handling EPAM, service discovery, encryption, load balancing, and multi-host connectivity, all without extra provisioning. Using an industry-standard Wilks main data plane, the overlay driver separates the container network from the physical infrastructure, ensuring portability across cloud and on-prem environments. With centralized control via Docker X, you get robust policy management, visibility, and security for large-scale clusters. Another benefit of the overlay network is that scaling is simple. Swarm and X networking automatically distribute traffic, ensuring seamless load balancing as you add more web containers. The MacVLAN network is the third type of Docker network. It assigns unique MAC addresses to containers, making them appear as physical devices on the network. This lets containers bypass the Docker bridge and communicate directly with the host network interface. In this example, the DB and web containers are on separate MacVLAN networks, each with an external IP from its respective network. MacVLAN is ideal for scenarios where containers need direct access to the physical network, such as integrating with legacy systems, meeting strict compliance requirements, or avoiding network address translation, or NAT. This setup lets operators manage network policies externally and segment containers at layer 2. Alternatively, both containers could share VLAN by placing them on the same MacVLAN network. It's really useful in environments with tightly controlled IP management or where containers must mimic standalone devices, like in financial services or IoT setups, and that's it. Bridge, overlay, and MacVLAN networks are Docker's three main network types. Now you're ready to choose the best network for your applications. Overview of other Docker network types. Even though these are less common, there are a few more network types that you should be aware of. Let's start with the none network type. It provides a completely isolated environment for a container with no network connectivity. This disables any external or internal communication, making it ideal for tasks that don't require networking, like running secure, standalone batch jobs or testing applications in isolation. Containers using the NUN network can still perform tasks internally, but they can access or be accessed by other networks. This ensures maximum security and control for specific use cases. The IPLN network is another type. It allows containers to share the host network interface, assigning each container its own IP address directly on the physical network. This setup bypasses the bridge, providing high performance and simplifying integration with existing network configurations. IPLN is ideal for environments requiring strict IP address management, things like legacy systems or tightly controlled enterprise networks. It enables better traffic segmentation and scalability, while maintaining compatibility with traditional network policies and tools. The final network type for us to talk about is host. It allows a container to share the host network stack, giving it direct access to the host's network interface. This eliminates the need for virtual bridges or network address translation, providing minimal latency and improved performance. It's ideal for applications requiring high throughput or real-time communication, such as game servers or monitoring tools, but since it bypasses Docker's network isolation, use cases should prioritize trusted environments where performance outweighs the need for container isolation. This course will focus on the most common network types, but you can look at the Docker documentation for more information on NUN, IPLN, and host networks. In the next section, we'll look at the most common network types in action. Docker network types in action. Now that you have a good grasp on the bridge, overlay, and MacBoolean network types, let's take a look at them in action. Since the bridge network type is the default, there are no necessary customizations or flags needed when you run a container. Here in the terminal, I'm going to run 3 separate containers using the docker run command. First, we'll run a Postgres container. Type docker run, the D flag, then this name flag set to database. Add the E flag to set the Postgres password environment variable to example. And use the Postgres latest image. Next, we'll run a Python container. Again, type docker run the D flag and set the name to backend. Add the environment variable for database URL and set it to Postgres, then a colon, and 2 forward slashes, followed by database port 5432 MIT. then use the Tiangoli Oski ink flask Pithrami 8. And finally, we'll create an ink container. Type docker run bit flag and set the container name to fondant, add the p flag, and map port 8080 on the host machine to port 80 in the container. Use the ink latest image. Let's list the networks using the docker network ls command, and you should see the bridge network. To make sure that these containers are running on the bridge network, we can use the docker network inspect command and the name of the network, which is just bridge. You should see the 3 containers we're running listed here. You can also create custom bridge networks, and we'll cover that in the next chapter. At this point, we can stop and remove each container before we move on to overlay networks. Next, for the overlay network, we need to initialize Swarm using the docker swarm init command. Overlay is a swarm scope driver, which means that it operates across an entire swarm or UXA cluster, rather than individual hosts. Next, we'll create an overlay network using the docker network create command, a driver flag set to overlay, and name it my overlay net. Let's run docker network ls to make sure our network is present. It is. Now let's deploy services and attach them to the overlay network. In this case, we're creating 3 services and using this network flag with the name of our network. These services are database, backend, and frontend. You can copy these commands from the cheat sheet in the GitHub repo for this course and paste them into the terminal. The services may take a few minutes to run. Once that's done, we can use the Docker network inspect command to verify that the containers are running on the same network, which they are. Before we move on to MacVLAN, you'll need to remove the services we created using the docker service ram command. Then leave the swarm using the command docker swarm leave and this force flag. The MacVLAN network type allows containers to appear as individual devices on the physical network. First, in the Docker desktop terminal, create a MacVLAN network on your host using the docker network create command. Set the driver to MacVLAN, and then set the subnet, which defines the IP address range for the network. This gateway option specifies the gateway for the subnet. The containers connected to this network will use 192.168.1.1 as their gateway to communicate outside the subnet. The O option specifies the parent interface on the host system that the MacVLAN network will bind to. Here, SRO is the physical or virtual network interface on the Docker host that connects to the network. And finally, name the network MacVLAN network. Again, verify that the network exists using the docker network ls command. Now let's run 2 containers using the MacVLAN network. Type docker run then the dflag and the name of the container DB. Set the network to the MacVLAN network, and then assign the IP address. Add the Postgres password that is required, and use the latest Postgres image. For the second container, name it backend and set the network and IP address. Add the database URL and use the InkFlask Python image. Again, use the Docker network inspect command to verify that both containers are running on the MacVLAN network. Before we move on, you can delete the running containers in Docker Desktop. Let's also remove the unused networks by typing docker network prune. Great job! In the next section, you'll have a challenge to help reinforce what you've learned in this chapter. In this challenge, you'll be given a scenario and questions to reinforce your learning about types of networks. The topic for this challenge is isolated database and web containers on the same host. Here's the scenario. You're deploying a web application with a database on the same Docker host. The web application needs to access the database, but you want to ensure that these containers are isolated from other applications running on the host. The containers should be able to communicate with each other, but not with external applications, unless explicitly exposed. Which network types should you use to isolate these containers while still allowing communication between the web app and the database? What benefit does this network type provide compared to others? That's it. Good luck on this challenge, and in the next section, I'll show you what I came up with for the solution. Let's review the solutions for this challenge. In this challenge, I asked you to consider a scenario where you're deploying a web application and a database on the same Docker host. And the containers need to communicate with each other while remaining isolated from other applications on the host. I asked you to answer the following questions. Which network types should you use to isolate these containers while still allowing communication between the web app and the database? What benefit does this network type provide compared to others? A bridge network should be used in this case because it allows containers on the same host to communicate with each other while keeping them isolated from the host's external network. The bridge network ensures that the database container and the web container can communicate with each other using container names, which Docker automatically resolves via internal DNC. However, containers on the bridge network are isolated from containers on other networks and from external traffic unless specific port mappings are configured. This is ideal for applications where you want containers to be isolated, yet still need them to communicate with each other. That's it. Congratulations on getting through this challenge. In the next section, we'll learn about creating and managing custom networks. Creating a custom bridge network. Working with the default bridge network is okay for quick testing or in development environments where networking complexity isn't a concern. It works out of the box for basic container-to-container communication on the same host. But what if you're working on multiple projects and projects with multiple containers that need to communicate with one another? That's where custom bridge networks are necessary. A custom bridge network is similar to the default bridge network, but provides more flexibility and control. With a custom bridge network, you can assign specific IP addresses and custom settings. You can also control which containers can communicate with each other. Custom bridge networks are ideal when you need isolated networks for your containers, or if you want to set up more complex configurations with multiple services interacting. Let's take a look at some of the options available when creating a custom network. In the terminal, type Docker network create, and then the help flag. Driver specifies the network driver. Since the default is bridge, this can be omitted when creating a custom bridge network. Gateway IP sets a custom gateway IP for the network. IP range specifies a specific IP range from the subnet to assign to containers, and subnet allows you to set a custom subnet, which controls the IP range for containers on this network. Now let's create a custom network with the subnet option. The command is docker network create, the subnet option, and I'm going to set this to 192.168.1024 and the name custom bridge. Suppose you're building a multi-service application with a web server database and cache server. You want these services to be able to communicate with each other securely, but without exposing them to the public internet. You will run each service with the network flag to attach them to the custom bridge network. Now, the web server, database, and cache server can communicate with each other on the custom bridge network, but they're isolated from other containers on different networks. To confirm these containers are communicating, we can ping from one container to the other. To do this, we're going to run one more container using the Alpine image, which already has the ping command assigned to path. Now we can run the command ping dvrs. You should see the results of the ping command showing the Alpine container is receiving bytes of data from the dvrs container. Note, the IP address is within the IP range of the subnet that we provided when we created the custom bridge network. To stop the ping command, you can type crfc. And that's it. In the next section, we'll discuss managing network connections. Managing network connections. Until now, we've added the network to our containers using the docker run command. In this section, we'll focus on connecting and disconnecting containers from Docker networks using multiple networks and best practices for organizing and securing your containerized environment. The Inc., MySQL, and Redis containers from the previous video should still be running. First, let's create a new network named Custom Bridge using the Docker Network Create command. We can connect the existing web server container to this network using the Docker Network Connect command, then the name of the network and the name of the container. In Docker Desktop, click on the running web server container and click the Inspect tab at the top of the screen. Click on Networks. Here, you can see that the web server container is using both networks that we've created. Attaching a network to multiple networks refines communication, enhances security, and supports a modular architecture. It can serve external clients on one network while accessing sensitive resources on another. Different networks may enforce distinct firewall rules or access controls. This layered approach improves isolation, reduces unnecessary exposure, and simplifies maintenance. By bridging multiple tiers, a single container can securely interact with various components, ensuring better organization and scalability across complex applications. Let's look at how to disconnect. To disconnect a container from a network, use the Docker Network Disconnect command with the name of the network and the container name. Go to the Inspect tab for the web server container to verify that the network has been disconnected. Even though the network was disconnected, it should still exist on your system. Even though the network was disconnected, it should still exist on your system. You can verify this using the Docker Network ls command. It's a best practice to clean up any unused networks using the Docker system prune command. Enter Y when prompted, and you should see that the custom Bridgestone network has been removed. There's another way to remove unused networks. First, let's stop and remove the running containers in Docker Desktop by clicking the Delete button next to the names of the containers. Type Docker Network Ream Custom Bridge to remove the unused network, and you can confirm that both networks have been removed using the Docker Network ls command. Effective Docker network management involves clearly defining and organizing your networks using meaningful descriptive names to quickly identify network purposes. Isolate sensitive services like databases on internal-only networks and expose only what's necessary externally. Employ multiple smaller networks to maintain logical separation and limit cross-communication. Routinely remove unused or outdated networks to keep the environment lean and secure. By combining thoughtful segmentation, strict access rules, and continuous oversight, you can maintain more resilient and maintainable Docker network architectures. It is time for another challenge. In this challenge, you'll create a custom bridge network, run a container, and then connect and disconnect it from the network. And finally, you'll remove the network. First, create a custom bridge network and name it My Custom Bridge Network. Next, run a container named WebApp. Run it in detached mode and use the Inc image. Do not attach it to the network yet. Connect the network to the running WebApp container, then disconnect the network from the running WebApp container. The last step is to stop the container and remove My Custom Bridge Network. Good luck with this challenge. See you in the next section, where I'll walk you through the solution. Let's walk through the solution to the challenge. In this challenge, I asked you to create a custom bridge network, run a container, connect and disconnect it from the network, and remove the network. First, I asked you to create a custom bridge network and name it My Custom Bridge Network. This can be accomplished using the Docker network create command and the name My Custom Bridge Network. Then I asked you to run a container named WebApp in detached mode with the Inc image. Do not attach it to the network yet. You can do this using the docker run command, followed by the D flag, and then name it WebApp, and the name of the image, which is Inc. The next step was to connect the network to the running WebApp container. The way to do this is to use the docker network connect command, followed by the name of the network, which is My Custom Bridge Network, and the name of the container, which is WebApp. Then I asked you to disconnect the network from the running WebApp container. For this, you would use the docker network disconnect command with the network's name and the WebApp container's name. Then remove the network using the docker network rem command and the name of the network, My Custom Bridge Network. Great job on this challenge. In the next section, we'll talk about container communication and DNC resolution. Using Docker DNC for container discovery. Now that we've discussed the different types of network drivers and how to connect containers to networks, let's talk about the underlying connectivity using Docker's built-in domain name system, or DNC. Docker's DNC simplifies container communication by letting containers use names instead of hard-to-manage IP addresses. This is especially useful in dynamic environments where containers are frequently created, destroyed, or scaled. When containers are attached to a user-defined bridge network or an overlay network, Docker automatically provides a built-in DNC service. This DNC enables name resolution, meaning containers can reference each other by their names rather than relying on static IP addresses. By default, when a container is launched with a specific name using the name flag, Docker registers that name with its internal DNC system. Containers on the same network can use that name to communicate seamlessly. DNC-based communication eliminates the need to hardcode IP addresses, which can change when containers restart or scale dynamically. Imagine an environment with multiple containers running microservices. If one container needs to connect to another, using IP addresses is problematic because IPs change when containers are recreated. Managing IP addresses manually doesn't scale for modern applications. Docker's DNC resolves this by dynamically updating name-to-IP mappings for containers on the same network. You can simply refer to a container by its name. Let's talk about how to leverage Docker's built-in DNC for container discovery. First, let's create a custom bridge network named My Network. Docker's built-in DNC works seamlessly on user-defined networks because it supports automatic DNC name resolution. This creates an isolated bridge network called MyNetwork. Docker uses its networking stack to manage this network, assigning IP ranges and enabling DNC for containers on it. Next, we need to attach containers to the custom network so that they can resolve each other's names. We'll do this using the docker run command. We'll create containers for Inc, MySQL, and Alpine. The Network MyNetwork option attaches the containers to the custom network. Docker DNC service registers the container names, app and DB, and their IP addresses within the network. When you run the pingdb command, Docker's internal DNC resolves the container name, which is DB, to its dynamically assigned IP within the MyNetwork subnet. Containers run an isolated network namespace connected via virtual Ethernet pairs to the bridge network. The bridge network routes Internet Control Message Protocol, or ICM ping packets from the app container to DB. The DB container responds, and Docker routes the reply back, completing the communication all within the isolated bridge network. You can type crethc to exit the shell. In the next section, we'll discuss the benefits of Docker's built-in DNC and some real-world examples. Benefits of the built-in Docker DNC. Docker's built-in DNC makes it easier for containers to communicate by automatically matching container names to their IP addresses. It's really valuable in dynamic, scalable, and distributed environments. Here are some scenarios where Docker's DNC excels: microservices architecture with microservices. Services like API and DB need to communicate seamlessly. If a container restarts or scales, DNC updates automatically, ensuring no disruptions. Scaling services. When services scale horizontally, IP addresses change automatically. Docker DNC registers all instances under the same network, enabling smooth load balancing. For example, a load balancer routes traffic to backend services by name. CCD and development environments. Docker DNC ensures consistent connectivity across development, testing, and production. Applications reference container names, making configurations environment agnostic. For example, an app container connects to DB locally, and the same name works in production. Distributed systems. In multi-host environments like Docker Swarm, DNC ensures seamless communication across hosts using overlay networks. An example could be a web app on host A that connects to the cache on host B using the service name. Zero downtime updates. Updating a container is smooth when services reference names. For example, replacing the app container with a new container keeps connections intact as DNC updates automatically. Docker DNC makes things simpler and more flexible, which is why it's so important for modern applications that use containers. Connecting containers with aliases. In multi-service applications, containers often need to communicate seamlessly and adapt as the environment scales. Docker's network aliases offer a powerful way to simplify container communication by providing alternate customizable names for containers. This flexibility ensures that your setups remain clean, predictable and adaptable as the application grows. A network alias is an additional name assigned to a container within a Docker network. Aliases allow containers to be referenced using multiple names, providing a layer of abstraction that simplifies communication between services. Containers within a Docker network can have their default name, for example, API, and one or more aliases like backend or servicing. Other containers on the same network can communicate using these aliases instead of the default container name. Aliases are useful when services need multiple references or when transitioning from one service name to another without breaking connections. Let's take a look at this in practice. First, let's make a new custom bridge network named MyBridgeNetwork. Next, we're going to use the docker run command to run two containers connected to the MyBridgeNetwork network. The first one will name DB, then specify the MyBridgeNetwork network, and then we'll add a new flag for network alias and set it to database. We will finish with the SCLA password environment variable and the MySCLA image. We will repeat this to create an Nginx container, and this time we'll use the network alias frontend. Now the DB container has an alias of database, and the Nginx container has an alias of frontend. This means that these containers can be referred to as either the default name or the network alias name. To test the network connectivity, we're going to run an Alpine container and connect it to the MyBridgeNetwork custom network. Let's open the shell so that we can use the terminal. If you ping DB, you should see some bytes being returned from the DB container. Now stop it, press Ctrl+C. Now ping database to get the same result, verifying that you can use either the default container name or the network alias. Note that the IP address is the same for both ping commands, which tells us that we are pinging the same container, but with different names. And we can do the same for the app container. Ping app and you should see communication with the app container. Ping frontend, and you'll see the same communication using the same IP address. Now we can remove our containers before we move on to the next section. Type exit to exit the shell, and then click the delete button to the right of each container name to stop and remove the containers. Network aliases have a significant impact on how you structure and manage multi-service applications. A single service can have multiple aliases. This is useful when one service fulfills multiple roles or needs backward-compatible references during migrations. In the next section, we'll discuss managing custom networks using Docker Compose. Managing networks using Docker Compose. Until now, we've managed our network connections by running single containers one at a time, but if you're working with a multi-container solution, you would use Docker Compose instead. Let's take a look at how networks are managed using Docker Compose. Here I have a composed YAML file in a directory named Docker Networking. I'm using VS Code as my IDE, but you can use the IDE of your choice. You can find this file in the GitHub repository for this course. At the bottom of the composed file, I've specified a custom bridge network and set the driver to bridge. You can use any network driver that we've talked about here, including overlay, NACVN, none, etc. I have two services set up, one for the app and the other for the DB, just like we did in the previous section. Both containers are using the custom bridge network, and I've set the alias for the app service to frontend and the DB service to database. Now we can open a terminal in VS Code and run one command docker compose up and the D flag to run it in detached mode. This will create the custom bridge specified in the network section. You do not have to create it using the docker network create command, then the containers are attached to the network and the proper aliases are set. Note that the name of the custom bridge network that was created is actually Docker custom bridge. This is because Docker creates the custom network using the name of the folder where the composed file is located. Now we can do a Docker network inspect for the Docker custom bridge network. You can see here that the default names of these containers that are attached to the network also include the name of the folder containing the compose file. Back in Docker Desktop, we can inspect the DB container and go to the network settings. Here you can see that it is connected to the Docker Networking custom bridge network, and the aliases are shown. In Docker Desktop, let's shut down the containers we just created before running our next test. Since we use Docker Compose, we just need to delete Docker Networking, and that'll also delete the other containers. You can also override the default name by adding the custom project name to the top of the compose file. Here I'm naming my project my app. Now if we run Docker Compose up again, we should see that the default network name is now preceded by my app instead of Docker networking. This is just another way that Docker allows you to customize naming conventions to make things easier to manage services and networks. In the next video, I'll give you a challenge to test your understanding of the topics presented in this chapter. You should stop and remove your containers in Docker Desktop before proceeding. In this challenge, you will create a new custom bridge network and run 2 containers on the same network. To verify communication between the containers, you'll set a network alias and ping one container from the other container. First, make a new custom bridge network named My Custom Bridge Network. Next, run a container in detached mode and name it WebApp. Connect it to the My Custom Bridge Network you just created and give it a network alias named Frontend. Use the ink image. Run another container in shell mode and connect it to the My Custom Bridge Network. Use the Alpine image. In the Alpine container shell, ping the WebApp container using the network alias. Bonus points if you can answer the question, which names can you use to ping any container attached to the same network? That's it. Good luck on this challenge, and in the next section I'll walk you through the solution. Let's walk through the solution to this challenge. First, I asked you to make a new custom bridge network named My Custom Bridge Network. This can be done with the docker network create command and entering the name My Custom Bridge Network. Next, you need it to run a container in detached mode and name it WebApp. Connect it to the My Custom Bridge Network and give it a network alias named Frontend. Use the ink image. To do this, you would use the docker run command with the D flag and then this name flag with the name WebApp. Add this network flag and set it to My Custom Bridge Network. Use this network alias flag and name it Frontend. Then use the ink image. Then I asked you to run another container in shell mode and connect it to the My Custom Bridge Network. Use the Alpine image. This can be accomplished using the docker run command followed by the it flag, and then this network flag set to My Custom Bridge Network. Add the Alpine image and sh to open it in shell mode. And finally, you needed to ping the WebApp container using the network alias in the Alpine container shell. Since the network alias is Frontend, the command you need to enter is ping Frontend. You get bonus points if you can answer the question, which names can you use to ping any container attached to the same network? You can communicate between containers using either the container name, which is WebApp, or the network alias, which is Frontend. That's it. Good job on this challenge. In the next section, we'll talk about troubleshooting Docker networking. Common Docker networking issues. When you're working with Docker networking, you're bound to run into some issues. In this section, we'll take a look at some common issues and how to resolve them. One of the most frequent problems in Docker networking is when containers can't communicate with each other. By default, Docker containers on the same bridge network can talk to one another using their container names as DNC addresses. However, if your containers are on different networks, this breaks communication entirely. Sometimes even when containers are on the same network, DNC resolution can fail due to configuration errors. Another common cause is an issue with the bridge network itself. If it's not set up properly or it's corrupted, traffic between containers can be interrupted. When containers are isolated in this way, your services and applications can fail to connect, so verifying the network configuration is critical. Another common problem arises when containers experience port conflicts on the host. This happens when multiple containers attempt to map to the same port on the host machine. Docker doesn't allow two services to bind to the same port simultaneously, so the conflict prevents one or both services from running correctly. This issue often occurs when static ports are hard-coded using the pflag during container startup, and you're unaware that a port is already in use. For example, if two containers both map to port 8080 on the host, only one will succeed while the other fails. Managing port assignments carefully is essential to prevent these conflicts and ensure that all of your services are accessible. Sometimes you'll notice that a container cannot access the internet. This can break updates, API calls, or external dependencies. This issue often stems from misconfigured DNC settings inside the container. If Docker's DNC resolver isn't working correctly, the container won't be able to resolve domain names. Another culprit can be the firewall or iptables rules on the host machine, which might block outbound traffic from Docker's network. This often happens when custom firewall rules are set, without accounting for Docker's default behavior. Without external connectivity, your containerized applications lose access to critical resources. Another frustrating issue occurs when services running inside a container are unreachable from the host machine. This usually happens for a few reasons. The ports aren't exposed properly, or the service inside the container is bound to 127.0.0.1 instead of 0.0.0.0. By default, if a service listens only on the container's local host 127.0.0.1, the host won't be able to access it even if the ports are mapped. Another potential issue is forgetting to map the container port to the host port during startup. Without proper port mapping or service binding, the application running in the container remains completely isolated and inaccessible. That's it for the most common networking issues. In the next section, I'll walk you through how to troubleshoot and fix networking errors. Essential Docker networking commands. Docker networking errors can prevent containers from communicating with each other or with external systems. In this section, I'll walk you through a step-by-step process to identify and resolve common networking issues using basic Docker commands. Back in VS Code, open a terminal. When troubleshooting, start by checking the available networks and their configurations using the docker network ls command. This command shows the list of networks including bridge, host, none, and any custom networks. Look for the network your containers are connected to. You should see the MyApp custom bridge network that we used in the previous chapter. If you don't see the network, open the compose file in VS Code and run docker compose up and the dflag. You can also inspect a specific network using the docker network inspect command and the name of the network. This displays details such as the containers connected to the network, IP addresses, and the network driver type. Look for discrepancies such as missing containers or incorrect IP addresses. If a container is not listed, it may not be connected to the network. In this case, you can inspect the container either using Docker Desktop, as we've done before, or using the docker inspect command and the name or ID of the container. Look for the Networks section in the SON output. This section shows the container's network connection, IP addresses, and network name. Some key details to verify are the correct network, name, and ID. aliases, IP addresses within the expected range, and DNC names. If a container is not connected to the correct network, you can manually attach it. First, you should disconnect the container from the network using the Docker network disconnect command, then disconnect the name of the network and the container name. To verify that the network has been disconnected, go into Docker Desktop and restart the container. Then inspect the container again, and you should see that it is now connected to the default bridge network. To connect the container to the MyApp custom bridge network, type the command docker network connect, and then the name of the network and the container. Then inspect the container again, and you should see that it is now connected to the MyApp custom bridge network. Networking issues can sometimes arise from unused or conflicting networks. You should make a habit of cleaning up unused resources to eliminate potential conflicts. Let's stop and remove the running containers by clicking the Delete button next to the container group name in Docker Desktop. This will not remove the custom network, which will cause errors if it's not cleaned up. The first way to clean up unused networks is to use the Docker network prune command. This removes all unused Docker networks. Before running this command, ensure that no critical networks will be removed. Alternatively, you can remove unused containers, networks, and volumes using the Docker system prune command. This command removes all stop containers, unused networks, and dangling images. You'll need to confirm the changes before proceeding. By inspecting networks, checking container configurations, and pruning unused resources, you can troubleshoot and resolve many basic Docker networking errors. Always validate changes by testing connectivity between containers and external systems. This systematic approach ensures a clean and reliable networking environment in your Docker setup. In this challenge, you'll run containers connected to a custom network and troubleshoot network connectivity errors. First, there's a file named Compose Challenge YAML in the Docker networking folder. You can find this in the branch named 5.3, the GitHub repo for this course. Create and run the containers for this challenge by typing the following command in the terminal in versus code docker compose, then the F flag followed by the name of the compose challenge, YAML file, and the command up. You should have two running containers, EMPNI1 and BNI1. A custom network was also created by the docker compose up command. What is the name of the custom network? One of the containers is not connected to the custom network. Which one is it? Once you have identified the container that is not connected to the network, connect the container to the custom network. Verify that the container is connected to the custom network. Good luck with this challenge. I'll walk you through the solution in the next section. In this challenge, you ran containers connected to a custom network and troubleshooted network connectivity errors. First, I created a file named Compose Challenge YAML in the Docker folder. You ran the containers using the docker compose command, then the F flag, followed by the name of the Compose Challenge YAML file, and the command up. This should result in two running containers, EMPNI1 and BNI1. A custom network was also created by the docker compose up command, and I asked you the name of the custom network. You can find this information using the docker network ls command. This will list all networks created on your system. The custom network for this challenge is Docker Chulhan Custom Bridge. One of the containers was not connected to the custom network on purpose, and I asked you to identify it. You can view all of the containers attached to a network using the docker network inspect command, followed by the name of the custom network, which is Docker Chulhan Custom Bridge. The container that is not listed here is the DBIMU1 container. Now that you have identified the DBIMU1 container that is not connected to the network, connect the container to the custom network. This can be done using the docker network connect command, followed by the name of the network, Docker Chulhan Custom Bridge, and then the name of the container, Docker Chulhan DBIMU1. And finally, I asked you to verify that the container is connected to the custom network. You can do this using the docker network inspect command and the name of the network. You should see both containers listed here. Great job on this challenge. In the next section, we'll wrap up this course and discuss the next steps in your learning path. Course recap and key takeaways. In this course, you learn Docker networking essentials to aid you in ensuring that your containers are communicating properly. We also talked about basic troubleshooting tactics. We discussed the types of network drivers available, including bridge, overlay, ACVLN, IPLN, host, and none. We've reviewed the purpose of each network type and their use cases. I showed you how to create a custom bridge network using the docker network create command. You learned how to connect containers to a custom network using the docker network connect command. We also talked about disconnecting containers from custom networks using the docker network disconnect command. I walked you through how to manage your custom networks by listing them using the docker network ls command. We've reviewed network settings using the docker network inspect command. We talked about inspecting networks and containers and troubleshooting errors. We reviewed removing containers by running the docker network rem command, and we talked about removing unused networks using the docker network prune command. We discussed how effective Docker network management involves clearly defining and organizing your networks using meaningful, descriptive names to quickly identify network purposes. It's important to remember to routinely remove unused or outdated networks to keep the environment lean and secure. We've reviewed the underlying connectivity using Docker's built-in DNC. I showed you how the built-in DNC simplifies container communication by allowing containers to use names instead of hard-to-manage IP addresses. This capability is especially useful in dynamic environments where containers are frequently created, destroyed, or scaled. We talked about how network aliases impact how you structure and manage multi-service applications. A single service can have multiple aliases. This is particularly useful when one service fulfills multiple roles or needs backward-compatible references during migrations. I showed you how Docker Compose simplifies network management for multi-container setups by automating network creation and enabling secure isolated communication. We talked about how Docker Compose allows seamless service discovery via service names. It supports custom configurations, improves scalability, and ensures reproducible, efficient deployments. This makes inter-container communication straightforward and manageable with minimal manual effort. And finally, we discussed common Docker networking issues, including container communication failures. These are often caused by misconfigured networks, DNC errors, or corrupted bridge networks. Port conflicts occur when multiple containers map to the same host port, preventing services from running. Containers may lose internet access due to DNC misconfigurations or host firewall rules. Additionally, services can become unreachable from the host if ports are improperly mapped. Careful configuration and troubleshooting ensure smooth connectivity. We learned a lot in this course. In the next section, I'll provide you with additional resources for you to continue your learning journey. Solidify your Docker knowledge. Now that you understand the basics of Docker networking, let's talk about the next steps you should take to help solidify your Docker knowledge. If you haven't already, you should go through the courses included in the Docker Foundations. These courses are designed to provide you with the knowledge that you need to work with Docker in a professional setting. This course covers Docker basics, container management, image creation, troubleshooting, and best practices, enabling efficient, consistent deployments across environments. My course on Docker Fundamentals walks you through containerizing an existing web app from scratch. This course covers how to set up your development environment, write a Docker file, build and manage custom images, and run your Docker containers. Learning Docker Compose course explains how Docker Compose simplifies managing multiple Docker services, addresses local development challenges, and explores its capabilities, limitations, and advanced features for efficient multi-container setups. Another good course is Docker for Developers. This course teaches you how to leverage Docker for application development, from setting up containers and managing multiple services with Docker Compose to deploying apps in the cloud. This course covers Docker fundamentals, Kubernetes clusters, Docker Swarm for scaling, and continuous integration practices for efficient scalable deployments. With these courses, you will learn everything you need to know to be a successful Docker developer. Thank you very much for watching my course. I hope you enjoyed this course and found it helpful for your career.